I'm Roland Minton. These are some of my favorite math stories. In this episode, mathematics is rare. We'll look at two surprising results, one important and the other, well, honestly, irritating. In other episodes, we've talked about how counterintuitive probability calculations can be, and this episode won't help any. We start with a sequence of problems that tortured several of us in Trexler Hall for, well, too long. All three problems had to do with meeting someone who has two children with the assumption that boy-girl births are essentially random and 50-50. The first question is easy. If you know that the older child is a girl, what's the probability that both are girls? You're probably thinking 50%, and you're right. Now, what if all you know is that at least one of the children is a girl? What's the probability that both are girls? If you're still thinking 50%, this time you're wrong. It's 1/3, 33%. Finally, what if what you know is that one of the children is a girl born on Tuesday? What's the probability that both are girls? If you think that Tuesday is irrelevant and the answer should remain 1/3, I'm sorry to say that you're wrong again. It's 13/27. I can explain why these are the answers, and we'll do so in a second. But to be honest, I'm still a little hazy about the big picture of how these three puzzles fit together. Well, let's look at one child being a girl. The possibilities for two children are boy-boy, boy-girl, girl-boy, and girl-girl, with each being equally likely. Knowing there is one girl eliminates BB, and the two-girl case of GG is 1 out of 3 remaining possibilities. The probability is 1/3. Well, what changes if one child is a girl born on Tuesday? To use this information, the possibilities now should list sex and day. We have boy on a Monday followed by another boy on a Monday followed by boy on a Tuesday, and so on. Quite a long list. Well, let's eliminate all the pairs that don't include girl on Tuesday, and that dramatically shortens the list. We have girl on Tuesday followed by girl on Tuesday, or followed by girl on Wednesday, girl on Thursday, and so on. Or the girl on Tuesday could be second with girl on Wednesday, and so on first. That's 13 that have two girls. We also have girl on Tuesday followed by a boy on any of the 7 days, or the girl on Tuesday second, preceded by boy on any of the 7 days. 14 of these with one girl and one boy. 13 and 14, 27 possibilities. 13 are two girls, and the probability is 13 out of 27. Well, this accounting is undeniable, but why does specifying Tuesday as the birthday matter? I'll give some thoughts on that after another puzzle. You get tested for a rare disease, one that only 0.01% of people contract. The test given is 99% accurate, meaning that 99% of people without the disease test negative, and 99% of people with the disease test positive. Assuming everything is random, if you test positive, what's the probability that you have the disease? It's easy to think that the answer is 99%, but read the information carefully. If you have the disease, the test identifies that 99% of the time. Disease leads to positive test. This is different than the question here, which goes in the opposite direction. Positive test leads to disease. Like with the birthday problem, you might think that the rarity of the disease is irrelevant. It's not, and the answer is that it's less than a 1% chance that you have the disease. Instead of showing you the exact probability theory proof, let's keep it simple by thinking through an example. Suppose we have 10,000 people. Based on the disease rate of 0.01%, we would expect one of these people to have the disease. The test will almost surely show a positive. Now, the other 9,999 people do not have the disease. The 99% accuracy of the test means that 1% will show a false positive, which comes to 99.99 people, round it to 100. Of the 101 people getting a positive test result, only one has the disease, and 1 over 101 is a little less than 1%. Now, to be clear, the medical community knows about this calculation and has measures such as retesting the original sample to reduce the eventual level of false positives. But what can we learn from these problems? Hopefully, your takeaway is not that probability is nonsense. I'll agree you have to be careful and precise to avoid jumping to reasonable but incorrect conclusions. The common characteristic in these two problems is the rarity of a side event, born on Tuesday, having the disease, skewing the calculations. Why does Tuesday matter in the birthday problem? I can't give you a nice intuitive answer, but it does make the occurrence rarer, narrowing down the list of possibilities and pulling the answer closer to the baseline probability of 50%. In the false positives problem, the 99% accuracy of the test is pulled closer to the baseline probability of 0.01% of having the disease. Probability questions arise daily as we balance risk and reward in social, financial, and other situations. We sometimes struggle with the relevant probabilities because we want a logical and simple story to guide our thinking, but we often need a comprehensive listing of possibilities to get the right answer. Without confronting problems like these, we might not factor in how the baseline information available, especially for rare occurrences, affects the probabilities.